Tour is a free event that happens on the first Thursday of most months. The tour is produced and managed by the graduate students here at the University of Toronto Department of Astronomy and Astrophysics, and assisted by the generous funding from the department and the Dunlap Institute for Astronomy and Astrophysics. The tour is structured into two parts. First is a public lecture, which you guys are at. And the second is, following the lecture, we have simultaneously planetarium tours and telescope viewings upstairs in the tower. And I'll be giving instructions and information about those two activities following the talk. So I'd like to ask everyone to stay seated following questions. It's important information. So tonight we're pleased to present Dr. Adrienne Erickcek. Dr. Erickcek received her PhD from Caltech in 2009 and now holds a joint postdoctoral fellowship at the Canadian Institute for Theoretical Astrophysics and the Perimeter Institute in Waterloo. She is also a junior fellow in cosmology, in the Cosmology and Gravity program at the Canadian Institute for Advanced Research. Her research spans a number of areas of theoretical cosmology, including modified gravity, gravitational lensing by dark matter, and inflation. These are all very heady topics, and tonight she'll be bringing some of them down to earth. Because Dr.
Hopefully.
Ouch. Dr. Erickcek will be exploring the history of our universe, or at least our understanding of it, cosmology, and explaining why inflation, a sudden, extremely short, and somewhat violent expansion of the universe very early in its life, has such a crucial effect on what we see today in the universe. Dr. Erickcek.
Thank you. Thank you very much for inviting me to speak tonight. Let's start with the history of the universe, because I'm a cosmologist and I always have to start with the history of the universe. I'm a little muted because I don't have a laser pointer yet. Hopefully one might arrive. But you can see the Earth. We are there. And we look out into our cosmos and we see galaxies. We look back further, and sometime eventually we hope to see maybe the first stars. We look out even further, and we see this cosmic microwave background, which I'll be talking about in great deal over the course of the lecture. And from our observations of this cosmic microwave background, we conclude, we guess, that there was an instant shortly after the Big Bang where the universe had a growth spurt. And that growth spurt is called inflation. It was an instant of extremely rapid expansion, less than a tiny fraction of a second after the Big Bang. Now, how do we know all this? Why should you trust me? Well, the cosmologist toolbox has two major ingredients. One is electromagnetic observations. We use it all: the optical, the X-ray, and of course, the microwave. Second is the fact that we can measure how many light elements there are in the universe, like helium and lithium and deuterium. And the quantity of those elements tells us about the conditions of the universe 2 to 3 minutes after the Big Bang. So first, let's talk about the electromagnetic observations and what do they tell us. They're particularly useful because looking out in the cosmos is the same as looking back in time, because light takes a finite amount of time to reach us. So for instance, when we look up at the stars in our galaxy, the ones you might look at tonight up in the telescopes, we're seeing them as they were 4 to 65,000 years ago, because they're 4 to 65,000 light years away. We go out even further and we see other galaxies. We see them as they were 2.5 million to 2 billion years ago. And because they're up to 2 billion light years away. Now you notice these numbers are starting to disagree. And that's because the universe is expanding. So we see them as they were 1.9 billion years ago, but they're actually a little bit further than 1.9 billion light years away from us, because they've been moving away from us after they sent us their light. This discrepancy gets even more apparent when we consider the really faint galaxies we can see. We can see them far away because they're very, very, very bright. These are the luminous red galaxies. And we see them out to almost 5 billion light years. We see them as they were 4.1 billion years ago. Even brighter are the quasars. These are extremely, extremely luminous objects in the centers of galaxies. And we can see them out to 28 billion light years, or as they were 12.8 billion years ago. And even furthest out, we have the cosmic microwave background, which is basically out to the age of the universe, which is 13.7 billion years old. However, the CMB, the area we see when we see in the CMB, is currently 46 billion light years away from us, because it's been moving away after it sent us the light. Now, one of the tools we use to depict this is called a light cone. And this is a little strange. Time now is on the vertical axis, and space is on the horizontal. So we sit at the top, and we look back in time. And we look back in time to other galaxies and quasars. And ideally, we would like to look back in time all the way out to the Big Bang, right there at the bottom. But we can't, because this cosmic microwave background gets in the way. That's the furthest that we can see. Now, we can't see anything on either side of this cone, because the light from those regions hasn't had time to reach us yet. So we can only see what's in our little light cone. Now, I've mentioned that the universe is expanding. This is the major grounding principle of cosmology. And because we see the universe expanding, we're tempted to run the movie backwards. So let's say you have a box with some stuff in it. And you want to know what's the energy density in that box. Well, it's the number of things you have times their mass divided by the volume of the box. So if I expand that box, I increase its volume, I don't increase the amount of stuff in it. So the density goes down, like 1 over volume, or 1 over the radius, the distance, the length of the box to the third power. Now what if instead of having like balls in my box, I had light? Well, light behaves a little bit differently. You can think of light as photons. When I increase the size of my box, my photon density goes down just the same, but something else also happens. All the wavelengths of the photons also get stretched. So not only are my photons being diluted, they are also being weakened. They have less energy per photon than they used to have. And that means the energy density in radiation falls off even faster, like 1 over the 4th power of the side of the box. Since the energy density in radiation is basically a measurement of the temperature of the universe, what this is telling us is that as the universe expands, it gets colder, constantly getting colder. So if we run the movie backwards, a young universe is a very, very, very hot universe. How hot? Well, I've plotted here basically a picture of what I just described. Energy density as a function of the size of the universe. So as the universe increases in size, the radiation density, this orange curve, goes down. The matter density goes down a little bit slower. And then dark energy, which we'll come back to, is just flat. So we look at where we are today. And today, 13.7 billion years after the Big Bang, our universe is created of 73% dark energy, 27% matter, and a teeny tiny little bit of radiation out in the many, many decimal points. The temperature of this radiation is now 2.7 Kelvin. That's 2.7 degrees Celsius above absolute zero. But if we run the movie backwards, what we see is that early times, it was all radiation. It was 100% radiation up at early times. And the temperature, 100 seconds after the Big Bang, was 1 billion Kelvin, 1 billion degrees. So what happens when the universe is 1 billion degrees? The entire universe is like the center of a very, 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 very big hot star. Well, let's look at what our universe contains. So here today, which is on this side, we have our current universe. Our current universe has us in it, people. It has galaxies, it has some black holes, and it has a little bit of radiation, the little squiggly lines. We look back, we see stars and galaxies, also a little bit of radiation. We look back and we see atoms. You look back further, it's too hot for atoms now. We just have a plasma, basically flame. You go back further and you start getting into the really exotic land of particle physics, where matter as we know it no longer exists. Now, the earliest point that we can really talk about with authority is this period 2 to 3 minutes after the Big Bang. And I mentioned the quantities of the light elements. So this is the epoch of Big Bang nuclear synthesis, when before this epoch, it was so hot and so energetic that you just basically had protons and neutrons flying around. But eventually the universe cooled, and so the protons and the neutrons were able to find each other and form a helium nucleus. And then we can go out and measure how much helium there is in the universe, and that tells us that this happened. The detection of primordial helium, helium that did not come from stars, was one of the first major pieces of evidence for this hot Big Bang theory. It tells us that in the early universe, the universe reached temperatures of 1 billion degrees. The next major source of information, like I've mentioned before, is the cosmic microwave background. So this was created 375,000 years after the Big Bang, when the universe was a steamy, but not quite so fireball-y, 3,000 degrees. What happened here is that before that, the universe was hot enough that there were no atoms. The electrons and the nuclei were separate. But then the universe cooled. The electrons were able to find nuclei and form atoms. And that's really important, because that's when the universe became transparent. When you have charged particles flying around, these protons and electrons, photons can't move very far. They move a little bit, and then they bounce off a charged particle, and then they move a little bit and bounce off another charged particle. They're trapped. But when atoms formed, suddenly the universe was clear. There were no more charged particles. It was like the clouds parted. And all these photons that were trapped, bouncing around in the early universe, started traveling in straight lines. And they started traveling towards us. And that's what we see as the cosmic microwave background. It is an afterglow from this era of extreme heat in the early universe, before there were atoms. So to give you a little bit of perspective on what we see when we observe the cosmic microwave background, let's take a trip through our Milky Way until we reach us. There we are. And we look out, we see the sky all around us. We make a little map. Just like a globe, a map of the world unfolding, we unfold out our map, and you see the galaxy there in the center. If we go down to longer and longer wavelengths of light, down to the microwave, we start seeing this uniform glow. We have to dial up the contrast a lot before we start seeing features. And then we see this. This is the cosmic microwave background. The red is the galaxy. Boring. We subtract that off. The rest of it is telling us what the universe looked like in its infancy, what the universe was like 375,000 years after the Big Bang. So a little history of the CMB, because it is the cosmologist's favorite light source. It was first detected in 1965 by Penzias and Wilson, who were not looking for it. They were IBM technicians, and they were just trying to build a really, really, really sensitive radio antenna. And no matter how much they tried to get all their systematics under control, they kept on getting the same little static. They were very annoyed. They tried everything to get rid of the static. Nothing they would do helps. And so they started talking to people. And eventually somebody pointed them that you really should call the guys at Princeton. I think they were looking for something like this. And yes, indeed they were. David Wilkinson at Princeton was leading a team to go out and find the cosmic microwave background. And so Penzias and Wilson give him a call and say, hey, we're told you might be able to help us out. We got the static. It's coming from all directions. We don't know where it's from. And Dave Wilkinson hung up the phone and said, well, boys, we've been scooped. Penzias and Wilson got the Nobel Prize in 1978. The theorists who predicted that the cosmic microwave background would be there did not get the Nobel Prize. And we're still a little bitter about that. The 2006 Nobel Prize again went to the experimentalists. You'll notice a trend here. For COBE, which flew in 1992. And this was important because this was the first detection of fluctuations in the CMB, besides just the galaxy. These actual hot and cold spots outside of the galactic plane. A better map of these hot and cold spots came later in 2000 with Boomerang. A big balloon flew from Antarctica. They found that the fluctuations have a characteristic size. That characteristic size is 1 degree. And if you squint, you might be able to see it on this picture. All the blobs have about the same basic size to them. And that's going to be very important later. This is the current state of the art. This is WMAP. The W does stand for David Wilkinson, the guy who was scooped. So he got something. The galaxy here has been removed. This is a snapshot of what our universe looked like shortly after the Big Bang. Now, what should you see here? Well, there are hot spots and there are cold spots. But the key is that delta T that gives you this color scale is in microkelvin. It's at the millionth of a degree. These hot and cold spots aren't very hot and cold. For the most part, the CMB is perfectly uniform, with a temperature of 2.726 degrees Kelvin. There are just these tiny 1 part in 100,000 temperature fluctuations, hot and cold spots in different parts of the sky. But these temperature fluctuations have a characteristic size, like I mentioned before, about 1 degree. Now, the cosmologists really love the CMB, and so I thought I'd bring some toys to show you how much I love it. We like to cuddle it when we go to sleep at night. We play with it when we go to the beach. We love the CMB, and this is why. The CMB tells us a lot about our universe, and it was the first indication that maybe the hot Big Bang isn't the whole story. Mystery number 1 of the CMB. How is it so perfectly uniform? How did it get to be the same temperature? Remember my earlier discussion of the light cone? We sit on the top, we look back, and we see way off in the distance the CMB. We can only see things inside our light cone. But every point on the CMB has its own little light cone. That's these little different colored triangles here. The key here is that those triangles don't overlap. So the purple triangle had no way to talk to the blue triangle, and the green triangle had no way to exchange information with the brown triangle. But somehow, all of these little triangles knew to be exactly, almost exactly, the same temperature. To put this another way, because the size of these little triangles on the sky is that characteristic size of 1 degree, when we look at the CMB, every 1 degree patch is effectively an entirely separate universe that never ever communicated with any other of the 1 degree patches. And yet they all have exactly the same temperature. How did that happen? Mystery number 2. The CMB tells us about the geometry of the universe. And the reason is we know what that 1 degree means. It's the size that it's the distance light can travel between the Big Bang and the birth of the CMB. So we know how big that distance is. Think of that as the yellow burrs here. Now the angle that yellow burr corresponds to on the sky depends on the overall geometry of the universe. If we live on a sheet, like in the middle, it's just a basic triangle. Adds up to 180 degrees. But if we live in an open universe, which is shaped like a saddle, or a closed universe that's shaped like a sphere, that same yellow burr corresponds to a smaller or a larger angle. And that would change how we see the CMB. The way we measure this is this quantity omega, which is the energy required in the universe divided by the energy required to make it flat, like a sheet of paper. And the CMB tells us that that quantity equals 1.005 plus or minus, we don't know anything for certain, 0.007. It's really close to flat. But it gets worse. Flatness is an unstable point. It's like discovering that the universe is a pencil balanced on its tip. Because if you're a little bit off from flat, if you're a little bit closed or a little bit open, as the universe evolves, it will become more closed or more open. So the fact that it's so close to flat today means it must have been really, really, really flat during the Big Bang. In fact, the difference between omega and 1 at the time of BBN is less than 10 to the minus 16. Really, really flat. This means that the universe has exactly the right amount of energy in it. If the universe just had 1 extra photon for every 10 to the 16 other photons, we wouldn't be here in our universe today. Mystery number 3. Why does the CMB have fluctuations at all? So what I've plotted here is a tool that we use to study the CMB. It's called a power spectrum. What we do is we plot the temperature fluctuations as a function of the angular separation. So we go out and we measure all the points that are like 2 degrees apart on the sky and take the temperature differences and plot the average temperature difference on that scale. And then we go out and we measure 3 degrees on the sky and plot the average temperature difference on that scale. And that's how we build our power spectrum. So the fact that there's a big peak here at about 1 degree, that's this fact that the CMB has a characteristic scale, this 1 degree scale. Everything on smaller angles than that is plasma physics. It's sloshing around. We think we understand it. What's mysterious here are these fluctuations on the really, really largest angles. These fluctuations are on hugely separated parts of the sky. Where did they come from? No plasma physics can cause them. In fact, if you run the movie backwards and subtract out the plasma physics and ask what initial conditions must have been there to create this spectrum, it looks like this. It's just flat. That means that no matter what the angular separation, the average temperature distance is always the same. Where did these fluctuations come from? And why are they the same for all separations? So those are the 3 mysteries of the CMB that first told us that maybe something was wrong with our picture of the hot Big Bang. Why is the CMB so homogeneous? Why does it have the same temperature in all directions? Why is the universe so flat when this is an unstable configuration? And where did the tiny little fluctuations in the CMB come from? And what I'll explain is that inflation answers all of these questions. But let me briefly mention that the CMB also tells us something else. The CMB tells us about the energy content of the universe. And this is so strange and so bizarre, I would be a terrible terribly remiss as a cosmologist if I didn't mention it. Only 4% of the universe is in electrons, protons, atoms, everything you learn in chemistry class. So next time you're struggling in chemistry class, or if you've forgotten all of your old chemistry background, don't worry about it, it's only 4% of the universe. 23% of the universe is dark matter. This is some kind of stable, neutral, at temperatures of 3,000 degrees Kelvin, particle. No known particle fits this description. So it's something else, it's something different. We don't know what it is yet. But the fact that it's there is not only supported by the CMB, it's also supported by galaxy motions. And I'm sure you'll hear about that next month in Dr. David Law's talk. 73% of it, like I mentioned before, is dark energy. Yeah, we're clueless. No idea what this stuff is. It has some kind of negative pressure. It's driving the universe apart. It's forcing the universe to accelerate. Supernova observations back it up. We have no idea what it is. So, let's talk about inflation. Quick lesson in general relativity, because a lot of cosmology is general relativity. Einstein tells us that gravity is actually the curvature of space-time. Mass curves space-time like a bowling ball sitting on a rubber sheet. And then space-time tells mass how to move. We orbit the sun because the sun makes a big indentation in the rubber sheet, and our orbit is the closest we can come to a straight line. Applied to cosmology, what general relativity tells us is that the content of the universe determines how the universe expands. So if the universe is filled with matter, it follows this blue curve for size versus time. If it's filled with radiation, it follows the red curve. It expands less quickly. The key with both of these curves is that the velocity of the universe's expansion, its expansion rate, is decreasing. The universe is decelerating. And that makes sense, because gravity is trying to pull everything back together. It's like you threw a ball up in the air. Its velocity is going to decrease as it moves away from you. The same is true with the universe. Gravity is trying to pull everything back together, so that initial energy from the Big Bang is being slowly bled away. So the key here is that both radiation and matter, they both decelerate the universe. So let's look at the radius of our observable universe as a function of time. Notice the extreme scales on both axes here. Here we are now. The size of our observable universe is 47 billion light years. At the time of the CMB, it was smaller. When helium formed 2 to 3 minutes after the Big Bang, smaller still. This is the highest energies we can reach with the Large Hadron Collider you may have heard about in Switzerland. Still smaller. And if we had believed the hot Big Bang model, we would have just followed the straight line all the way back to time of 0, all the way back to the Big Bang. But we don't. Instead, we do something rather dramatic. We say we follow the blue line, and we insert inflation. That the universe's volume doubled at least 260 times in an instant. To give you an idea of what kind of growth spurt this is equivalent to a proton, tiny, tiny proton, growing to be the size of the Earth's orbit, an astronomical unit, immediately. It's an exponential expansion. It has to be driven by something new. We call it a scalar field. Its major component property is that its energy density is not diluted as you increase the volume. I'll come back to that. And then inflation ends and we resume our hot Big Bang. Now this is a rather crazy idea. Alan Guth proposed it in 1981. And over the past intervening 30-odd years, it has become an essential ingredient of modern cosmology. And here's why. It solves the horizon problem. Remember, the problem was that all of the little light cones on the CMB all had different temperatures because they'd never talked to each other before. But what inflation does is it takes a tiny little patch of the universe and blows it up so that it covers our entire observable universe today. And now it's no longer a mystery why all of those triangles have the same color. They're all connected via inflation to the same tiny little patch. It solves the flatness problem. So this is a page out of Alan Guth's notebook dated December 7, 1979. And it has here spectacular realization. This kind of supercooling can explain why the universe today is so incredibly flat, and therefore resolve the fine-tuning paradox. I really wish my research notebook had realizations like this in it. So how does this work? Well, remember I told you that being flat was unstable. It's like a pencil balancing on its tip. That's because if the universe evolves, it will tend to become even more curved. But that's only true if the universe is decelerating. If the universe's expansion is accelerating, the curvature will decrease. And there's a simple analogy to understand that. Basically, imagine that the early universe is like this ball. And you can easily see that this ball is curved. But what inflation does is it basically takes this ball and turns it into the Earth. It's very difficult to see that the Earth is curved. The Earth appears flat when you're on it. And that's what inflation basically does to the entire universe, is it makes it look perfectly flat, no matter how curved it was initially. Inflation also tells us where those fluctuations came from. It's all quantum mechanics, folks. All the galaxies you see, all the stars, it's just quantum mechanics writ large on the sky. And that's because quantum mechanics tells us that if we zoom in to empty space isn't so empty. There are little energy fluctuations constantly popping in and out of existence. Now normally, like in this room, these quantum fluctuations pop in, they pop out. They pop in, they pop out. We don't even notice them. You have to look really hard to detect them. But during inflation, that story is very different because the universe is literally expanding so fast that when a quantum fluctuation pops in, it's stretched out before it can pop back out. Moreover, think of these quantum fluctuations as a little wiggle all the time. And we start at the bottom here with this little red wiggle. And then we wait a little bit. The universe is expanding, and it's expanding fast. So that red wiggle now has a longer wavelength. But quantum fluctuations are still going on, so we have the blue wiggle on top of it. And we see the sum. You wait a little longer. Now that red wiggle is very stretched out. The blue wiggle is intermediate. And we now have a new wiggle on top of it. And it's this way that inflation lays down the same exact initial perturbations on all wavelengths, just like we observe in the CMB via quantum mechanics. So, this is a happy story. Why do I still have a job? Well, there are some unanswered questions. What drove inflation? Why did the universe experience this growth spurt? Why did the universe behave in such a strange way? Well, it was a scalar field called the inflaton. And what's the inflaton? It's the scalar field that drove inflation. Yeah, we don't know what it is. We're looking. How big is our inflationary patch? This is an important question because it speaks to how long did inflation last. We don't know. It's at least as big as our observable universe. We don't know how far beyond that it goes. What was the universe like before inflation? Yeah, we're clueless. The problem is that inflation is like a big eraser. It wipes the slate clean. Now on one side, this is good, because it can take a messy, violent Big Bang and turn it into the nice, pristine, happy universe we see all around us. But it's also bad because it erases all the evidence of the Big Bang. We don't know what happened before inflation. And how did inflation start? Yeah, this is a really good bedtime story to tell your kids. The inflaton, once upon, started nearly at the rest of the top of a nearly flat potential slope. And yeah, that's not a very satisfying beginning. We'll get into that right now. So the answer is we need more information. What are we doing to try to learn more about inflation? Well, let's start with the inflaton. Meet the inflaton. First of all, what is it? It is a scalar field, okay? What does that mean? Well, a field is just something that has values everywhere in space. You might have heard of the electric field or the magnetic field. A scalar field is the same, except it just has a value at every point in space, not a direction. Now, the energy density in a scalar field is basically given by its potential, which I've plotted here as V. So that you can think of the scalar field as this little ball. And it's rolling on a little slope, this potential. Most of its energy is in the fact that it's lifted off the ground. And that's when inflation happens, is that this potential energy is nearly constant. As the little ball moves, as inflation progresses, the height of this potential stays fixed. And that's important because it means, like I mentioned before, that if I take a box of inflaton and I increase the size of my box, I have the exact same energy density in my box as I did before I increased the size. It doesn't dilute at all. This is really strange. And because this is strange, it can power inflation. So going back to general relativity, our friend Albert here, the universe's size as a function of time, I showed you what it looked like for matter and radiation. For the inflaton, it looks very, very different. There's our accelerating universe. And it's because of this special property. Now, what about those quantum fluctuations? Well, what those quantum fluctuations are is they're little spots where the inflaton is a little bit ahead or behind. Like I've drawn here, the little ball can be a little bit ahead on its path or a little bit behind in different parts of the universe. Different values of the inflaton corresponds to different energy densities because while the potential here is flat, it's not perfectly flat. And those different energy densities give you different temperatures in the CMB. So when we look at the cosmic microwave background, we're seeing the quantum fluctuations of the inflaton. Well, great. So we know a lot about the CMB. It's our best friend. Surely we can use it to tell us what the inflaton is. Not quite. Because the CMB temperature fluctuations give us some information, but they don't give us all the information we need. What the temperature fluctuations in the CMB tell us is basically the potential energy of the inflaton divided by the inflaton velocity. This is helpful, but we really would like to just know V itself, the energy density during inflation. That would tell us where to go tell the string theorists to start looking. If we knew that the inflation happened at 10 to the 15, 10 to the 16, 10 to the 12, GeV, that at least would give us a clue of where should we be looking for new physics to understand inflation. But we don't know even where to look yet. Luckily, there's hope. During inflation, the inflaton isn't the only thing that gets quantum fluctuations. Space-time itself gets quantum fluctuations in the form of gravity waves, little ripples in the fabric of space-time itself. And those ripples leave a very distinctive pattern on the CMB, namely its polarization. Do you have polarized sunglasses ever? And you rotate them, you can see that reflected light is often polarized. That's why polarized glasses reduce glare. We can do the same thing with CMB. And the gravity waves leave a distinctive pattern in the polarization that we can use to measure the inflaton energy density. And the search for this polarization pattern is on. It's happening right here at University of Toronto at the team led by Barth Netterfield, looking for this particular pattern. We wish them all the best of luck. Another way we have to study inflation is to look very, very carefully at the CMB. And you can think of the CMB hot spots and cold spots as following a bell curve. So some of you are probably in college. You're probably really familiar with bell curves. The average here of the black line is kind of a C. Some people get B's, some people get D's. Very few people get A's, very few people get F's. A perfect bell curve is called Gaussian fluctuations. And it's possible that when you look at the CMB, it's very nearly Gaussian. Most of the points in the CMB have temperatures of the mean. But there are some hot spots and there are some cold spots. And the hotter the hot spot, the rarer it is. But maybe it's not perfectly Gaussian. Maybe it's a little skewed, like this blue curve. This blue curve would still have the average grade being a C. But notice there's more B's and fewer A's. This is like saying in the CMB that there are more kinda hot spots, but fewer really hot spots. And these deviations from Gaussianity can tell us about the physics of inflation. And the Planck satellite, which is up in the sky now, and hopefully we're going to get data from it very, very, very soon, is going to tell us how Gaussian the fluctuations are. And that hopefully will tell us about the inflaton. Now, I will have to briefly say, inflation is not proven yet. It's compelling. It explains a lot about our universe, but there are some competing theories. One is what I'll call the null hypothesis. Maybe the Big Bang just made it that way. The truth is, we don't really understand the Big Bang. It's quantum gravity, and we don't know that yet. So maybe the natural starting point of a universe is just homogeneous and flat. With Gaussian scale invariant, that's the same on all wavelengths, fluctuations. The first part I might be able to swallow. The second part, not so much. I don't think the Big Bang could have started that neat. I don't know much about the Big Bang, but my gut tells me it was probably messy. However, there's a problem. It's not that easy to start inflation. So did we really make any progress here? Frankly, I don't think we can answer that question until we know, or at least have an idea, of what the inflaton actually is. There is an alternative, one proposed partially by Neil Turok, the director of the Perimeter Institute, so I think I'm contractually obligated to mention it. And that's what's called a cyclic or ekpyrotic model. Basically, the idea is that everything you get from inflation, you could get from the exact opposite. Inflation was a rapidly expanding universe. A slowly contracting universe can give you kind of the same thing. The thing is, though, our universe is not currently contracting. We know the universe is expanding. So if it was once contracting, it must have somehow bounced. It was contracting, and then it rebounded and started expanding again. That's not easy to do. That's the major challenge for these theories. And another extension to string theory I would like to mention is called eternal inflation and string theory. Basically, this is an idea that maybe inflation is the universe's default state, and only tiny little bubbles ever stop inflating. And we live in such a bubble. We might collide with other bubbles. The string theorists tell me that this would be very unpleasant. When one bubble collides with another bubble, one bubble loses. So we hope that our bubble is safe. And there are currently people, some of my colleagues at the Perimeter Institute, looking for imprints in the CMB of past bubble collisions. Obviously, we would have won those. Let me just conclude a little bit about dark energy, because there's a tantalizing connection here. Are we inflating now? Well, the CMB tells us that 73% of the energy this question mark here, is just unaccounted for. There's a little bit in radiation. There's a little bit in what I call baryons. That's, chemistry, 4%. There's a little bit in dark matter, and then there's a lot in something else. In 1998, there was a surprise, which led to the 2011 Nobel Prize. The universe is accelerating now. How do we know this? Well, we look at supernova. And the hope is, we're promised that, supernova are standard candles. Type 1a supernova to be exact. Every time they explode, they always explode with the same brightness. So if we look at supernova and we measure how bright they appear to us, that tells us how far away they are. And then we can also measure how fast they're moving away from us. And when we look at the supernova distance versus velocity, we see that the distant supernova are moving slower than we would expect if the universe only contained matter. The dotted line there is if the universe only contained matter. And all of the points are to your left of that line. They're moving slower than expected. And if they're moving slower than expected, that means that the Hubble expansion, the expansion of the universe, used to be slower than it is today. And that tells us that the universe is accelerating. And that's this dark energy. That's 74% of the universe. Maybe you noticed this on this plot I showed earlier. I pointed out now, and you see the blue curve is starting to shoot up. That's because we are currently accelerating. So, does the shooting up there have anything to do with inflation? It kind of looks the same on this picture. But there is a key difference. It's a very different energy scale. We don't know exactly the energy at which inflation happened. Like I said, we're working really hard to try to figure that out. But we do know that it's somewhere between about 10 million electron volts and 10 to the 16 billion electron volts. Kind of a wide range, I know. Like I said, we're working on it. We're working on it. But we know that dark energy is 0.002 electron volts is the characteristic energy scale of dark energy. It's really, really, really different. So trying to connect these two phenomena while tantalizing and tempting is very, very, very difficult. Believe me, I've tried. But there's still a little bit of a hint there that maybe these two things are connected. They do have a lot of similarities. Just like the inflaton, dark energy does not seem to be diluted by the expansion of the universe in any way. Some people say that dark energy is just another scalar field, just like the inflaton. Now there are two of them. We don't know. But the fact that the universe is accelerating today, and we think we're pretty confident that the universe accelerated shortly after its birth, it would be really nice to connect these two eras of acceleration. So I'll just end here with a little bit of cosmology humor. The following ad ran in Fermilab's newsletter back in 2008. It reads, "Mature paradigm with firm observational support seeks a fundamental theory in which to be embedded." Inflation is a beautiful idea. There's a very good reason why it's become part of our standard cosmology history. But until we understand the inflaton, until we know why it happened, we really can't call our work done. Thank you very much.